Okay, so we're going to, like I said, continue lecturing a little bit more here on this chapter, which I believe is 18 still, I hope. So we just started talking about really sort of kinetics involving radioactive decay. And as I mentioned before, right there before we ended, these are really the couple of important equations that we use in radioactive decay in terms of kinetics. This is really concentration versus time dependency sort of equation. So obviously, initial or final, where you started with or ended with, and how long you could really solve for it. And then obviously, like I said, very common in these problems, you do need to use both of these guys together, the half-life equation. And a lot of times, like I said, you would be solving perhaps for the decay constant or rate constant. Then you could go into here and solve for whatever else that you need. So a lot of times on these problems, you'll look at this equation and go, I'm missing two things, and they will give you that half-life. So you could use, again, that half-life equation to find one of the two things you're missing. Then they'll allow you obviously to solve for the last thing. So why don't we try one here? If you have a 1.35 milligram sample of a little plutonium 236, calculate the mass that will remain after 5 years. And radioactive decay, once again, going to follow that first order kinetics, which means these are really our equations we want to look at. Natural log of 2 divided by k. Now, in this particular case, we have 1.35 milligram sample, so that is our initial for sure. We want to calculate the mass that's left over, which would be our final, and we're going to do it for 5 years, which is our time. So again here, we are short the decay constant or rate constant there to allow us to solve for that. That is why I had to go dig out the other important information you should have had, which was the half-life. So we could use the half-life and the half-life equation to get to the decay constant, which would be, again, the last thing that we would actually need there. So if we do that, our half-life here would be equal to the natural log of 2 divided by k, which means k is the natural log of 2 divided by the half-life. That gives us our 0.693, which is what you get when you take the natural log of 2 divided by 2.86 years. And that gives us a decay constant of, we'll call it 0.2424. The units here are reciprocal years, yes. So again, 1 over a unit of time, which is what you would expect for first order kinetics. It's always 1 over something unit of time. The units of the rate constant or decay constant, whatever we want to call it. Also really important when we use this equation is to make sure that these two values here agree in terms of units. Sometimes they don't. So sometimes maybe your decay constants in years, maybe their one's in days or something like that. So the units of those things in terms of time, you do want to always watch out for that because sometimes they are not always the same units. Now that we do have that, we have pretty much everything we need. The natural log of A would equal the natural log of our initial 1.35 minus the decay constant we just solved for, reciprocal years, times the time, which is 5 years. So again, in this case, the years cancel. So we're all good in terms of units on that side. If we clean up on the right-hand side here, we're going to take the natural log of 1.35. We're then going to subtract it from 0.2424 times 5. Going to give us the natural log of A is equal to minus 0.9119-ish. To get rid of the natural log, we need to take the E of both sides, right? So do a little E action of both of those guys. When we do that, those guys are going to cancel. That's going to give us the concentration of A, or really our final guy will be do that. And we'll call it 0.402. The units here would match, obviously, the original units, which is milligrams as well. Question on that calculation? Yes, sir. How did I get, say again? Which one? 0.693. Oh, that should be the natural log of 2, I believe. If I'm not. Yeah, so when you hit natural log of 2 on your calculator, it's 0.693. Yeah. Is it? Yeah. So sometimes books will just do the 0.693, or sometimes they'll write natural log of 2, but that's basically how you get to it. Yeah. Other questions? We also could see if it sort of makes sense. This is obviously decay, right? Which means we should end up with less than what we started with. So obviously we did here. We started with 1.35 milligrams and ended with 0.4. So obviously that is less. Any questions on that? All right, so just under 2 half-lives should take us down half twice. All right, so why don't we try another one here? How about our friend radon-222? It's a gas that will leak into our houses. Fun. Assuming no loss due to leakage, there is 10.24 grams of radon in the house today. How much will be there in 5.4 weeks? The half-life of radon there is 3.8 days. Okay, let's take a look. So once again, we're going to roll with our first order equations. And in this case, we have a couple things. We have obviously the time. We do have our initial. We're looking for what will be there, right? In 5.4 weeks. So once again, we do need to get to our decay constant. We are given the half-life, and as was questioned earlier, you know, one of our times are in weeks and one of them are in days. So you do need to do a conversion. And again, it really shouldn't matter which way you go. You might be slightly off, you know, depending on, you know, some rounding, but it shouldn't really matter. And you can do it at any point. I'm just going to do it up front. So I think I'm going to take the weeks into days. So I'm going to take my 5.4 weeks. So fancy 5. And I believe there's still only 7 days in a week. And that would get me 5.4 times 7 would be good. About 37.8 days. Right. All right, so since I can convert that into days, I can leave my half-life into days and go into here and solve for K, which would be the natural log of 2 over my 3.8 days. That is going to get me natural log of 2 divided by 3.8. Gives me a 0.182 reciprocal days. So again, once again, the units are 1 over days, which is again 1 over time, which is what the unit should always be for the rate constant for a first order, 1 over time. At this point now, I got my days and days together. So we could go in natural log of A going to equal our natural log of our original, which was 10.24 minus our 0.182 reciprocal days times our 37.8 days. So once again here, the days will cancel. And cleaning up the right-hand side one more time, natural log of 10.24 minus 0.182 times 37.8 gives us the natural log of A equals minus 4.553. We're going to E both sides one more time. Going to give us really our final concentration here of, go with 0.0105 grams, I guess it would be in this particular case. Any questions on any of those there? Okay. So again, that is sometimes they trip up when people are using this equation. Both of these units are not or both of these guys are not in the same unit, so you really do want to watch that. Any questions on any of those two? This one we just did. There you go. All right, we can also use sort of first order kinetics to do radiocarbon dating or uranium 238 dating by using the half-life here of carbon 14, which is 5730 years. We can also use uranium dating, which will leave us some lead left over and some other guys here that has a half-life of 4.51 times 10 to the minus 2. Sometimes you take the difference of what is left over to sort of figure out how old something is. But we really can use the first order kinetics the exact same way that we did before, except in this case, we'd be solving for time, which would give us how old something would be. So let us take a look at one here to see how that works. An ancient skull gives 4.5. Those are units of disintegrations per minute per gram of carbon. That is not Celsius in this case. That's actually a gram of carbon. And if a living organism has 15.3 disintegrations per minute per gram of carbon, how old is the skull? So the importance of these units is the grams of carbon part. That's going to do a little carbon radio dating, which means for the half-life, we will want to use carbon 14's half-life, which is 5730. So why don't you give it a try, see what you come up with. 5730 being the half-life there in years. How old is the ancient skull? Again, you could use your first order kinetics just like we did before. We'd be solving for time. And take a look. So once again, going to roll with the same equation. Can't go wrong in nuclear chemistry to roll these equations if you're doing something like this. All right, in this case, we're actually given not really grams or concentration, but we are given rates of radioactive decay, which is obviously what disintegration per minute per gram of carbon is. And it works the same way, assuming the ancient dead one is the final, usually, right? And living would probably be initial, I'm assuming. Also, final probably should have less counts per minute, right? Because it has decayed for a while, right? So it shouldn't be giving off as much radioactivity. So that means we do have, again, both of these guys. We are solving for T like we talked about before. Just like on the previous ones here, we will use our half-life equation here to get to our decay constant, which in this case will be our 5730 years. Taking the natural log of 2 there, divided by 5730, going to give us something like 1.21 times 10 to the minus 4 reciprocal years. In this case, we're going to be solving for time, which means when we do, our units will end up being years in this case because of the decay constant that we have. At this point, we could put in what we have. Again, our final would be the smaller rate there. So natural log of 4.5 equals the natural log of 15.3 minus 1.21 times 10 to the minus 4 reciprocal years and T. Personally, what I do is take the natural log of 4.5 and then subtract that guy over to the other side. So I'm going to do the natural log of 4.5 hit equals minus the natural log of 15.3 hit equals. Going to get you a negative 1.22378 equals negative 1.21 times 10 to the minus 4 reciprocal years. Clearly, we're going to take this to the other side. The two negatives will cancel out, giving us a positive year. Also, the year on the bottom will flip to the top as you divide, and that will get you, approximately 10114 years, or like 1.01 times 10 to the 1, 2, 3, 4 years. About 10,000 years old. Pretty old, let's say in this case. Any questions on any of that calculation there? Can you leave it in this with the wrong number of sig figs? Probably. It's not a chemistry class. It's okay. No. Yeah, no, you'd probably be okay, I would think. Yeah. But right sig figs probably like 3-ish. Looks like everything else is 3, so probably ish is probably about right. Other questions on that? All right, let's try another one here. Archaeologists have dated a civilization to be 15,600 years ago. If a living sample gives 20 counts per minute per gram of carbon, what would be the number of counts per minute per gram of carbon of a rice grain that was found at the site? So once again, we are using carbon, which means we are rolling with the same half-life of 5730 years. Okay, so one more time here, we got also another unit of radioactive decay, counts per minute per gram of carbon, a little different than disintegration per minute per gram of carbon. So where you're going to use our equation here. We will also need to use our half-life equation, but since it is carbon, it will come out the same as what we had on the previous problem, which was 1.21 times 10 to the minus 4 reciprocal years. Again, that is found by taking basically the natural log of 2 divided by this guy, just like we did in the previous problem there. At this point, we're actually looking for this guy, I believe. How many counts per minute per gram of carbon there will be at the end there for our old piece of rice that we found there. So our initial guy is giving 20 counts per minute, and our K there with our reciprocal years, which is okay because our unit of time here is also in years. So once again, these guys will cancel out okay. Years will cancel. And again, cleaning up on the right-hand side here will get us, not that, natural log of 20 minus 1.21 exponent minus 4 times 15,600, going to give us the natural log of A equals 1.108. Whoa, come here. 1.108. If I didn't mess that up, try that one more time just to make sure. Looks good. Once again, we're going to take the E here, both sides, to get rid of the natural log, giving us a final count here of, looks like 3.03, and the units here would match the original, which would be counts per minute per gram of carbon in this case. We also see that the original one, right, is giving off 20 counts per minute, which is much more than obviously the piece of rice that's been sitting there for 15,600 years, which is giving off only about 3 counts per minute, as it's gone through obviously several maybe half-life, or has gone through decay in that case. Any question on kinetics and radioactive decay? All right, well, seems like a good stopping place, I think.